Hello everyone, my name is Divyanshu and we are very excited to present our final year project detecting arbitrage opportunity in S&P 500 options using unsupervised deep learning. This project represents a deep dive into the intersection of machine learning and trading. So to begin with the introduction of the project. First of all, we need to understand what an arbitrage is. So these are the opportunities that allow risk-free profit when pricing discrepancies arise in the financial market. So to address this, we propose developing an unsupervised deep learning model to detect arbitrage opportunities in S&P 500 options trading. Especially my focus is on identifying anomalies in the options pricing using key features like option Greeks. So to answer address what anomaly is, to basically whenever there is an unusual behavior or price movement in the market, we call that event as anomaly. So moving on to the next section, we talk about the data set, which is fundamental to our project. For this study, I will be utilizing the options chain data provided by the options DX platform. This includes the call and the put options data, option Greeks, implied volatility, market factors. The data set is quite extensive and granular, which allow us to capture even the smallest pricing discrepancy. So our primary objective and goal for this project is to design an unsupervised deep learning model which is capable of identifying price anomalies and finding hidden patterns in options pricing that indicate arbitrage opportunities. So to begin with, the project involves several key phases, starting with the data preparation and culminating into the development and testing the deep learning model. So now let's briefly understand the code that will drive our machine learning project. We begin with importing the essential libraries like pandas and numpys for our primary tools and data manipulation and analysis, matplotlib for the visualization of patterns in the data, min-max scaler we are using to scale down the data, and we are also using the TensorFlow libraries to construct our unsupervised deep learning model. Especially we build the model using input and dense layers, Adam optimizer, early stopping, etc. So in the next segment, we start by loading the data set that will serve as the foundation of our project. The data set is of S&P 500, contains options trading data that we need to analyze. We achieve this by using the pandas library and all of those stuff. So again, in the next segment, we focus on selecting only the numerical features that are most relevant for our analysis, because there are certain non-numerical and numerical data as well. To achieve this, we use a list comprehension to filter columns based on their data types. These data types typically represent numerical values such as features like a strike price, implied volatility, options prices, and other quantitative metrics. Next, we ensure that the quality of our data set by removing any rows with missing values. This is done by drop NF functions. Uh, in the next part, we focus on normalizing the data using min-max scaling. Um, to achieve this, we use min-max scaler is a scaler from the sklearn pre-processing library. We we have also got the data in the form of txt file, which we used for which we used the convert.py file, which used to convert that file into the csv file, which was a very lengthy, which took a lot of time. So this is the overall view of the options data and what it looks like and what are we going to analyze. So this was all about the options and the data sets and pre-processing of the data set. Now I would like to hand over the presentation to my teammate. So Shivam, over to you.
Hello, I'm Shivam, and let's move forward. Hello, I'm Shivam, and let's move forward with the model building. So to develop the unsupervised deep learning model, we will be using an autoencoder model for the use case. where we will be creating neural networks in which the autoencoder model learns to compress data into lower dimensional latent space and then reconstruct its back to its original dimension. So at the first we start, the input data has 24 features. So the first layer will also have 24 features. And to encoding, and we would set the latent space as 4, which is which means that there are 4 dimensions at the bottleneck layer. So then we begin with the encoding layer part, which will which will start with the input layer with 24 features, and the first layer would include 16 neurons with ReLU activation, and then the second layer reduces the number of neurons to 8, and then the third layer will have a neurons to number of 4, which will be the bottleneck layer. Then we will be using decoder, which will reconstruct the data, and it would go in the reverse order, where the first layer would have 8 neurons, then the second layer would have 16 neurons, and the last layer would have 24 neurons. And we would be using sigmoid activation function for that. And thus we will be creating an autoencoder model with Adam optimizer with a learning rate of 0.001 and a mean square error as the loss function to minimize the reconstruction error. With that, our model is ready. And to begin our training data, we would split the data set into 80 to 20 ratio, and then we would implement early stopping to not only save computational time but also reduce overfitting. With that, we will start training our model. So so as you can see, we have started the training model, but the thing is it would take a lot of time. So here is a pre-run data, pre-run code where I would be continue explaining. So early stopping was achieved after 3 epochs, and then we will start with an anomaly detection where where the scale data is passed through the autoencoder to generate reconstructed version, and then we calculate the mean squared error between the original and reconstructed data to measure how well the model captured and data patterns. Then we determine the anomaly threshold, which we have set as 95 percentile, and which will flag the anomalies and store that. And here is the histogram, which will shows the threshold and reconstructed error distribution. And then finally we will be saving the and we will be saving the anomalies detected. But how do we know our model created right now is good? So firstly we will be doing back testing. In this you can see that we have used the created data set for anomalies and to generate to generate a profit and loss for our data. And that we have generated a profit for a base capital of 10,000 ten, for a base capital, we have got a total returns of 49,802, whereas we have done a loss of $501. In comparison, if we do not use the anomalous data set and run it on the original data set, then we are only getting a total return of 47,794, whereas our maximum loss is $609, which has increased. Thus, we can conclude that our model is pretty successful and we are able to maximize our gains using risk-free opportunities. Thank you.
Thank you. It was soon like I said. If करूँ